In this video, I want us to expand on the idea of formal charge to something called resonance structures. But remember, it's all about trying to figure out an approximation of where these electrons are around the atoms, because that can help us understand a little bit about how the chemical is going to react. What's it going to do, what its properties are, and that's pretty important in the world of chemistry. And so with chlorite, which is what we've got right here, is there more than one Lewis structure? Yes. Is there more than one best Lewis structure? Well, let's see. Let's find out. All right, chlorite. Let's draw a possible Lewis structure. Chlorine has 7, oxygen has 6. There are 2 oxygens, but we have an extra electron because we have a -1 charge. So I'm going to put E and then 1. So I've got 12 plus 8 gives me 20 electrons that I can place around my structure. So chlorate. Chlorine is less electronegative than oxygen, so it goes in the middle, and then we put oxygen around the sides. We know we have 20 electrons. That means I need some electrons that are going to be going around my central atom, because I'm going to have 8 around my oxygens, and then I've got 4 more left over. 1, 2, 3, 4. Okay? So this is where I'm going to start with, but also because it is a charged particle, it needs a negative. So this is the skeleton. What are all my options here? Because I haven't filled in my dots yet. Okay, so could it be single? Yeah, that makes everything satisfied. And if I'd asked you before my last video, you might have said there's no other possibilities. That looks beautiful. Okay, but you know there are more possibilities. So you could go double bond, single bond. You could do triple bond. You could do double and double. But let's think through this for a minute. So before we looked and we realized we had formal charge oxygen as a single, which was different than formal charge oxygen as a double bond. What's my information here? Might as well check out the triple bond too. Let's do that one as well. So let's say we have a triple bond. What's my formal charge on a triple bond? It's 6 minus 2 dots minus 3 lines. So my formal charge on a triple bonded oxygen is going to be 6 minus 3 minus 2, which is +1.
Now you can't really see the structure I drew, which I apologize for, but you don't have a triple bonded oxygen. It doesn't exist, okay? And there's lots of reason for this. You can get into the electron configurations, the orbital configurations, that kind of thing, or you can kind of use your brain here. Why would oxygen, a very electronegative atom, ever want to have a +1 charge? It doesn't. And so using formal charge analysis, you can kind of help confirm that a triple bonded oxygen is just not going to exist.
All right, so what do we learn from that? We learn from that is that we're trying to make the formal charge on all of my atoms match the charge on my compound. So I've got 3 atoms here. What's the lowest possible configuration I can have that would allow me to have a -1? I could have a 0, and a -1. That's the lowest grouping of numbers. Because if I have a -1 and a -1, then something else has to be a +1. And that kind of spreads it out more. We want more and more of the atoms to be 0, if at all possible. All right, so one of these needs to have a -1 on them. Which one? Does it make more sense to have more of a negative charge on something that is more electronegative, or less electronegative? It makes more sense to have your negative on the atom that is electronegative, okay? Meaning, if I have a structure that has chlorine with a -1 and these two as 0s, that's not my best structure. I need it to be something that has 1 oxygen with a -1 and then a 0 on the chlorine and no charge on the oxygen, no formal charge there. So what's that going to look like? Well, if I just know a little bit here about oxygens, that's going to tell me I need 1 oxygen that's singly bound, and I need 1 oxygen that's doubly bound, and that's what I have drawn here. So if that's the case, this should be the most stable configuration. Let's add in my electrons, and let's calculate the formal charge on both of these molecules and check and make sure. So this one. Formal charge on a single oxygen, we're going to have a -1. On this one, -1. So therefore on this one, chlorine, 7 minus 4 dots minus 2 lines, I'm going to have +1. So you see how more than just one atom has a charge? That's not probably your configuration unless you need it to have 2 of them. okay? But normally, if you can have just one carrying the charge, it's better, unless you need two, okay? And we'll look at that in the next example. All right, so this one, I've got a double bond, 0. This one, chlorine, is 7 minus 4 dots minus 3 lines. It's going to give me 0 again. And this one, I've got a single. It's going to be 6 minus 6 dots minus 1 line, -1. So what that tells me is this is my most stable Lewis structure that I could make for my chloride ion. But wait, which one's more stable? This or this? You may be going, Dr. Hyatt, you have lost your mind. They look the same to me, they're just flipped. Well, this is a new term that's called resonance. And you indicate resonance by putting an arrow between the two possibly equally probable Lewis structures. What's really neat about this is they've done bond length studies to figure out which one or how long the bond length is. Because if you've got a single bond, that's a longer bond than a double bond. And so they said, all right, if there's only one configuration, it doesn't matter, then shouldn't one side of the molecule, the side that has the double bond, be shorter as opposed to the single bond, which is longer? Can we actually study the molecules and be like, ooh, this one's in this configuration, this one's in this configuration? The cool thing is, this bond length between the chlorine and the oxygen is somewhere between what you would expect for a single and a double bond. That's pretty fascinating, okay? It means that that electron is hopping between the two so quickly, or even you can think about the double bond. The electrons in this double bond are moving so quickly between the two oxygens that we cannot tell which oxygen it's attached to, and that's resonance. Resonance is when there's two or more equally probable Lewis structures that could exist simultaneously, okay? These aren't equally probable. Okay, you could, I guess, have one that's like 10% probable, but this case, no, not stable, okay? These two are in resonance, okay? These two are not. This one, bad, okay? These two, resonance structures, because they're equally probable. Which one's going to exist in nature? Yes, both of them are, simultaneously, if you will, okay? So this is a resonance structure. So if there's a third one, then I would just put another arrow and I'd put the next one out to the side, okay? But that's resonance. But we are allowed to use formal charge to help us determine what is our best structure, and then that will tell us whether or not we have resonance. I want us to do chlorate next. So go ahead and stop the video and try and draw what you think is the best Lewis structure for chlorate, and then come back and we'll all do it together. So chlorate, we've got chlorine with 7. We have oxygen with 6 times 3, and then we have an extra electron. All right, so 6 times 3 is 18, plus 8 is going to give us 26. So chlorine's my least electronegative. It goes in the middle. I have oxygen all around. I've got my brackets, my negative charge outside. And now I'm going to ask myself, do I remember all that stuff from before? Formal charge of oxygen is a single versus formal charge oxygen of a double. That's going to be -1. This is going to be 0. So that tells me how many formal charges do I need? Excuse me. So that tells me how many single bonds do I need? 1. I need to have 2. 2 doubles. Okay? Add in my electrons. Check and make sure I put all of the right number of electrons on my structure. I have not, because 8 and 8 is 24. I need an extra pair here in the middle. All right, is that all there is? Is this the best we can get? Let's check the formal charges and see if this is our best structure. So we have 6 minus 6 dots minus 1 bond, -1. Here I have 6 minus 4 minus 2 gives me 0. 0 for this one, and then chlorine, we have 7 minus 2 dots minus 5 lines gives me 0, and I'm good, okay? Do I have resonance? Absolutely. There are 3 different places. Your single bond could be here, here, or here. So there's 3 resonance structures for this molecule. Let's do another one. Let's do sulfate next. So sulfate, we have sulfur, which is going to have 6 valence electrons, oxygen, which is going to have 6 valence electrons times 4, and then we have extra electrons, charge of 2 this time. So we need 2. So 6 times 4 is 24, plus 6 is 30, plus 2 is 32. Sulfate's the least electronegative. It goes in the middle. 2 negative on the outside. Now that we've established this, let's just remind ourselves of our rules here. So with formal charge, I've got a single bond is -1, a double bond is 0. So I've got a charge of -2. So what does that mean? Does that mean one of them is -1 and maybe sulfur is -1 as well? Or maybe sulfur is -2? No. You need the more electronegative compounds, which in this case are oxygen, to have the more negative formal charge. So what that tells me is I have 2 oxygens with a charge of -1 and 2 with a charge of 0. Or another way of saying that is I need 2 double bonds and I need 2 single bonds. Okay? So let's try it and see if this will work. Put all of our electrons on there. Okay? Check and see if all of the atoms are happy. So we have oxygen here with 8, 8, 8, and 8. Sulfur has way more than 8, but it's greater than phosphorus, so it can have an expanded octet. Then check to see if you've placed 32 electrons on your structure. And we have 8 times 4 is 32. So I want to think this is the best, but let's double check with our formal charge analysis and see if that's correct. Single bonds are going to be -1. So this one has -1. This one has -1. This one has 0, and this one has 0. Sulfur. Sulfur is going to be 6 minus my dots minus my lines. I've got 6 lines. It's also 0. So is all of my formal charge analyses tell me that the formal charge on individual atoms adds up to be the formal charge on the molecule? And it does. So this is a good compound. Okay? The other things to check are your charges on the more electronegative elements? It is. We're correct. Okay? Now, do we have resonance? Yes. What's the other structure? Could be double bond, double bond. So we're going to have resonance with the structure that looks like this, with all of your electrons drawn in there. Okay? So the ideas here are we can use formal charge analysis to predict our best Lewis structure.